Good morning, students. Welcome to the mass transfer. Today will be lecture 23, and this is the gas liquid contracting equipment, and today will be last lecture. So today we'll discuss about the determination of column diameter, because last day I told if you can determine the column diameter, then according to the column diameter, what will be the stress spacing? It is almost fixed according to this tabulation. And we have seen for 1 meter column diameter, stress spacing is generally 1 feet, and around for 10 meter it is 3 feet. So, and from our process calculation already we have seen in the case of stage, if I make the number of triangle, I will get the each stage. So if in chapter 4 we have seen how many triangle we are getting between the operating line and equilibrium line, and according these are the number of stages, ideal stages. So if I calculate the ideal stages from this theory, and now if I know my column diameter, according to column diameter the trace spacing will be fixed. Let's take column diameter is 10 meter, then trace spacing is 1 meter. Is gap between two trays is 1 meter. So if I have a 30 number of ideal stages, so 30 into 1 meter, so my column height will be 30 meter and my diameter is 10 meter. So that's mean I have designed my mass transfer equipment, and this is my goal of mass transfer course. Now today we will see how to determine the column diameter. It depends on the what is the flooding velocity, and there is a way to calculate this one. Today we'll make this exercise with one problem. Here if you see, the problem is determine the column diameter of a sieve tray column for the separation of a mixture of benzene and toluene on the basis of following information. So I want to separate benzene and toluene in a sieve tray. For that one, what will be the column diameter according to this? Here liquid flow rate from the top, it is told that is 14,000 kg per hour. Bottom is 15,300 kg per hour. So these are the liquid flow rate. So from my process calculation, I will get this one, because if I know from gas phase to what is the flow rate, it will be vapor rate at the top 23,300 kg per hour, and bottom 24,500 kg per hour. Liquid density rho L is 810 kg per meter cube. Average vapor density rho average is 2.6.5 kg per meter cube average. Liquid surface tension is 20.5 diameter per centimeter. Temperature of the column is 82 degree. Average pressure is 18 psi. Generally, 15.4 psi equal to 1 atmosphere. So column, if it is open to atmosphere but inside little bit higher, that's 18 psi. Use the flow rates at the column bottom for design calculus. Okay, so for that here you calculate this and this bottom, because this is the thing you can take an average also, but once you do it, then it will not change. So if you want to get this one for this, so flow rates are given, gas flow rate and liquid flow rate for the operating conditions. Okay. Now you have to tell for this one what will be the column diameter. Now to determine the column diameter, there is fair method, okay, and there is one chart. Where this chart, one is CSB. Okay, CSB, this is flooding, this is the one constant, flooding constant, that is Sauder Brown constant at flooding condition as a function of flow parameter. And what is flow parameter? It is liquid flow rate by gas flow rate into rho g by rho L whole to the power 0.5. So I have this data. I know that liquid flow rate and gas flow rate. I have this density of gas and liquid average. So I can calculate this easily. Now I will take what? I will take the tray facing. So tray facing, but I don't know what is the column diameter. So I can take any of them. So this will be trial and error method. Let's take, I took the, let's take 12 inch. Then if I see the column diameter is 10 meter, so that's mean it is not correct. Then with this 10, then you recalculate this with 26, then what will be that? That will be that. So you have to match this one around that with this column. Otherwise, you have to take some trial and error method. So I will assume anything, one of this trace spacing, always better take in between. And then from this figure, I will guess the CSB constant. And once you will get the CSB constant, I will get the flooding velocity. This is the relation. And it is in feet per second. Keep it in mind. These are the correlations. Correlations means you understand there is no theoretical basis. People did the experiment and they developed this correlation which will be applicable to calculate your flooding velocity. Okay, so CSB, density, surface tension by 22 to the power 0.2, or rho L by rho g, it is in feet per second, whatever. Okay, so first let's calculate for this problem. Let's calculate this one, flooding velocity. Okay. So first flow parameter L by 0, this thing, this is bottom 15, this is the liquid flow rate, this is the gas flow rate, this is the density of gas, and this is the density of liquid. All are in. Okay. So now this flow parameter is 0.035, and if I take this 18 inch and 0.035, so it is coming around 0.28 with this 0.28. So this CSB will be this, and then this will be the flow, this thing. Okay. So from there, through this equation, you will get CSB equal to this in this part. So this equal to this divided by this part. Okay. So that's why it is into, it is like this. So then you can, from this thing, you can calculate what is the flooding velocity, that is 5 feet per second. That will come in second, 5 feet per second. Now that is the flooding velocity, but you cannot operate the column at flooding velocity. So let's take, this is a standard, you take the 70% of the operating velocity is 70% of the flooding velocity. So they are taking 70%. So then that operating velocity is 3.5 into 0.7, so 355. Okay. Now volumetric flow rate of vapor is this meter cube per hour, okay, and this is the conversion factor, okay, this is the density, because this is kg per hour, the density, the meter cube per hour, and this is the conversion factor, meter cube to feet cube, so this is the feet cube per volumetric. So if it is the volumetric, this is the volumetric flow rate, feet cube per hour, so this will be, then this by this, that will be feet cube by second by velocity 3.5 feet per second, so second, so then second will cancel out, so area is 25.9 feet square. Now this is the area, but you know, in total area, in the area you have to take some part for the downcomers, that is at around 20%, okay. So if it is 20%, so 25.9 1 minus fd, okay, fraction, what is the fraction, it is will be 0.8, so this is the 42.4 feet square. So this is the area. Now pi d square diameter, area equal to pi d square by 4, so accordingly if you count the critical diameter, this is 6.42 feet, means 1.96 meter. Now if you see 1.96 meter, 18 inch, 18 inch diameter, it is matching with this one. 2 to so this is the column diameter. So column diameter you have to calculate based on your flooding velocity, okay, and for that one you have to use this experimental quantity. So for a particular column, if you know the what is the column diameter, and if you know the how many trays are there, and if you know that what will be tray spacing, from tray spacing and number of trays you will calculate the height of the column. Here you are getting diameter of the column, that means you are designing your mass transfer. Thank you for your attention. Have a nice day.